Um, Perfect. So, welcome back, everyone. I hope you enjoyed the exercises so far. And, well, also thanks for solving the exercises. Also, for us, we really got something out of this. We have at least one new bug report and other interesting stuff to discuss internally. So, thanks for all the feedback that we got. So in the afternoon, as Carlos already mentioned, we are going to dive into some more advanced concepts. And actually, these are also going to be like gaps which need to be filled about discussions in the morning and things people noticed during the exercises. So what we want to cover in this afternoon, so this is both of my sessions. So somewhere in between here, we will break and we will mix it up with another hands-on, such that you don't have to hear me talking for another hour again, but you can do something in between. But what we want to cover is basically neighbor chains, like more general neighborhoods, sparse dimensions, which are special fields, which are of special location type, which we will discuss later. We will discuss how we can nest reductions, and we will discuss index fields, like fields which help us addressing stuff in the vertical. Then my colleague Giacomo is gonna take over and discuss some points or some further things which need to be clarified about the parallel model. And he's also going to conclude with maybe the most advanced topic with how we can do even vertical solvers with the dusk and dawn concepts. So let's dive right in. So you have seen these 6 neighbor chains, and there were already people asking if that's all there is. And the short answer is no, but let's go step by step. So first we are looking at an example which we have seen already, like from a node, you can go to the 6 neighboring cells. And as has been observed in, for example, in the icon code, this is not enough. We need more general neighborhoods. And this is what we call internally neighbor chains. Why chains? Well, here we are going to look at an example. We go from a cell to an edge. And then from that edge, I mean, nobody says we need to stop there, right? We could travel further. And this is exactly what we do. So from these 3 edges, we travel to all the cells we can reach from those edges. And again, nobody says we have to stop. We can travel even further. So maybe to these 7 vertices, which are reachable from the central cell. And now in the Slack, there was a very interesting discussion because you can like look at this picture from 2 different ways. You can start from the beginning and you can see this like as a growing neighborhood from the center. And this is kind of like our intuition why we list this direction in the first argument of the reduction. Because what's happening actually at the end of the reduction is not this direction of the arrows. It's actually the opposite direction. You take all these values and you draw them to the middle, so to speak, when you reduce. But I believe it's more intuitive in actually describing the iteration space if you start from the beginning. Like if you would list this as vertex cell, edge cell, then I would kind of like need to think backward to understand what kind of stencil I'm facing. But maybe that's just me. So if you have some input here, we're definitely looking forward to further discussions in the Slack. So why do we even need this? So as we have heard in the morning, like Icon is doing some higher order interpolation with wider stencils. So it's applied there. We have also found that also in Icon, but also more general, you can use finite difference stencils even on FVM meshes. And in this context, the neighbor chains are very helpful. And we also have potential use cases which we didn't see in the wild, but we could just imagine that this concept would be useful for that purpose, like wider FD stencils, where you not only look at your next two neighbors, or or some schemes which have very, very large stencils, like the essentially non-oscillatory schemes. Or for example, if you would not only consider the usual Galerkin methods, but the mesh-free ones, which will still operate on a mesh. But in these class of methods, the basis function is not confined to a single cell anymore. And then you could maybe describe this more general neighborhood, which then appears using the neighbor chain concept. So here we would like to look at a case study where such a concept might be useful. So here we are taking the RBF interpolation which we found in Icon. And in this case, we are not only considering values at the direct edge neighbor from a cell, but we are trying to improve the accuracy by looking at more neighbors. So here is part of the relevant Fortran code. So I think sometimes it's nice to look at the Fortran again to see where we are coming from, what we are trying to translate. You can see here that there are coefficients multiplied, which is obvious because we are in an interpolation. But let's briefly not look at them. We will dive into this in the next topic. But what we can really see here is that we have a wide neighborhood stencil with 9 entries, which certainly indicates that we are not facing only one of the simple neighborhoods where at most 6 neighbors can be encountered. So here we would have the same thing again, but manually translated into Dusk code. So again, we have these coefficients which have weird dimensions, but we're going to discuss this later. What you see here is that we sort of reverse engineered that, and we figured out that this Fortran stencils goes from saddles to edges, then to cells again, and to edges again to do this interpolation. So here I did nothing except I only isolated a single component because there would be U and V otherwise, and I shortened the notation a little bit such that it becomes more manageable on my slides. But now I want to quickly animate this example again. So here we can see how we build the neighbor chain. We start from the cell, go to the edges, go to the cells again, and from here to the next edges, and collect all the edges we found along the way. And these are all these 9 edges involved in that interpolation. So we multiply by the coefficients which we find on each edge, and then pull this in with the sum over concept. So here we are looking at the emitted pseudocode again, and we see that this is not more complex than what we encountered before. And this is because I generalized the neighborhood function in my pseudocode. So now this neighborhood function has not like just a signature where it says what we want, like cell neighbors, but we would have a second argument which can take like a vector of such cell edge, or more generally location tags. So to compare this to a simpler example before, like we even just traveled from a cell to an edge, we would reflect this on the right hand side here, and this was written like this earlier on. So maybe in a more practical world, this would have been implemented first, and then the programmer decided to introduce shorthands because this is obviously used more often later on in the development process. But yes, this is just to clarify what I am trying to, what kind of meaning I'm trying to attach to the pseudocode I'm showing to you. Okay, so these were the extended neighborhoods, the generalized neighborhoods. And a concept which is closely related, and one can hardly go without the other, is the sparse dimensions. And this was already inquired of in the morning, like where people asked that they see a weighting would more be part of the operand, and indeed sparse dimensions could exactly be a concept which could do just that. And we have already seen such sparse dimensions, and people were asking, so what is this strange location type specifier in these geometrical factors we have seen in the exercise this morning? And I hope I will now clear this up. And first of all, I want to explain the motivation of the name a little bit. So why are these things called sparse dimensions in the first place? And well, these are sparse dimensions because they can be implemented in principle like an adjacency matrix, which is sparsely populated along a dimension. So in case you never encountered the concept, we have a very simple mesh on the left-hand side here, just 3 cells, 7 edges, and we have the adjacency matrix on the right-hand side. And now you're telling me, well, this is not sparse because it's very populated, right? Like half of the elements. And yes, this is true. But if you're looking at a more general mesh, like for example, this architectural artwork on the left-hand side, and we are looking at the adjacency matrix of that one, we can see that only like 5% of the entries are not 0, but are 1, because there is obviously not every node is connected to every other node, but only on a small subset of nodes. So only a very small portion of each row will be populated. So in everything except the most trivial examples, the adjacency matrix is indeed sparse. So now how could we implement a sparse dimension with a sparse matrix? Well, sort of simple. Like if we wanted to compute the distance to the center for each edge, which is slightly pointless because this is an equilateral mesh, right? So the distance to the center for each edge is always going to be square root of 3. But basically, we could just replace the connected information, which is 1, by our value, which carries some meaning. And where we are not connected, we cannot put 0 anymore because, well, maybe not with the distance, but if it's something else, then it could also take the value 0, right? So we need to put something else like the empty set. Well, empty set is not an operator, but the empty set symbol. And, well, it's a little bit wasteful to implement it like this. So maybe we could just implement this as a higher order array. Like for each edge, we are storing 2 values. So for example, for the edge number 5, we store square root of 3 and square root of 3 because cell 2 and cell 3 have distance square root of 3. And now, if you compress it like this, obviously something is lost, like we don't have the complete connectivity information anymore. But this is very okay because we don't want to duplicate the connectivity information into each sparse dimension, right? It's also not something like how you would want to implement it. You would rather have this array representation, and then you would have the connectivity information stored in a meshing library, for example. Okay, so here this is just a summary slide. So we call these sparse dimensions because they could be implemented as a sparse adjacency matrix. But in for all practical considerations, you could probably assume that these are always going to be arrays of 1 rank higher than the rest, so to speak. I hope this will become clearer if we look at the worked examples. So for the people who were in the exercise this morning, they will certainly remember this, that we tried to compute the divergence. And when we are building this dot product here, we expect that the edge normal will always point outside, because otherwise we will not end up with a proper approximation to the divergence. Now, again, it turns out that if we want to store each normal only once, we can't really arrange our mesh in a way that this works out for all the triangles. So if you have two neighboring triangles, they share a normal, and we cannot make this normal point outside from the perspective of both of these triangles. And this is where a sparse dimension can come in. So we have this edge orientation, and the edge orientation for this red triangle would return 1, 1, and 1. So it returns 3 values because there are 3 edges to a cell, and it's always 1 because we never need to flip. When we compare this to the edge orientation at cell B, then we will have an entry of -1 because we need to flip the first normal we encounter. Another use case could be in interpolation. So here we have a formulation for interpolation, which is quite general. So here we have a function which takes the distance to the source points. Maybe let this rephrase just a little bit. So we want to interpolate from some points Q to a point P. And to do interpolation, we have interpolation weights. And these interpolation weights, they are somehow dependent on the distance of these points usually. So because I want to keep this general, I formulated a function W, which will take the distance to these points Q as argument. And for most any interpolation, if you're doing actual interpolation, not approximation, the interpolation weights need to add up to 1. And we can enforce this by dividing by the sum of all the interpolation weights. And then we get quite a general formulation for interpolation. And now maybe a question could be, can we do this without sparse dimensions in a first step? And it turns out, yes, you can. You can when your geometry is the same all out through your whole domain, and it's completely regular. And you have a spherical domain, or maybe phrased differently, that you have periodic boundary conditions. Like when you look out the boundary from one side, you come in at the other side, right? And if you want to do like a quite stupid interpolation where you just weight all your neighbors by the inverted distance, you could then do it by just using a weights vector. But that's not why we are here, right? We are here because we are interested in the more general case where the geometry is not completely regular all over your globe, which is the way more practical case. And in this case, we would in fact consume this additional coefficients sparse dimension. So here we have the same thing again, but this time we are looking at the generated code. And we can see that this sparse dimension appears because we multiply by it. It takes as a first argument the edge index because it goes from edges to some neighbors. And as a second argument, it takes a linear index, which in this case goes from 0 to 3 or from 1 to 4, because there are 4 vertices in an edge cell vertex neighborhood. Now I said beforehand that sparse dimensions are arrays with rank +1. And the question, of course, is +1 to what? Because if we are looking at this, we see that Fv and the sparse dimension have the same rank, namely 2. And now this is an artifact because we assumed, maybe reasonably enough, that the geometry is equal for each and every layer. If this wouldn't be the case, and we would for some reason have differing geometry for each layer, then we would also need to have a vertical extent for the sparse coefficient field. And in this case, you can now observe that indeed the coefficients array has rank 3, whereas the dense fields only have rank 2. Here we have the same thing again. I believe this is the example which we have seen before, the one transliterated from Icon, where we have, instead of just what we are talked about before, about this diamond, we have these 9 edge neighbors. And this would be the pseudocode that would be emitted in this case. And all that's different here is that we have a more complicated chain. And I think the point which I want to make here is actually after the break, it seems. So it seems like that we are breaking here and we are taking a first round of questions.
Thank you very much, Matthias. So let's have a look at the questions. So I will post again the link in the chat for everyone to have it at hand. So please pose your questions there. I mean, we're getting more into advanced concepts, so it's worthwhile to spend some time discussing it or to clarifying or asking Matthias anything that is not clear yet before we continue. No questions then? Someone is writing, so let's wait a bit. Right, so Rene is asking if you can explain, Matthias, where the coefficients, or maybe where and how the coefficients are calculated. You were explaining how to use them, but not how to compute them.
That's right. So short answer is this is what we will see after the break. Yeah, but maybe just there is a concept in Das Canton to do this, which we'll see in detail later. For now, you can assume that they are computed in the driver code, which would not be, I mean, assuming it would only, your sparse dimensions are only ever depending on the geometry, then this wouldn't even be an unreasonable choice, right? However, if they are dynamic, then you would need such a concept, and because they need to be, we are offering this. But yeah, more on this after the next exercise.
Mm-hmm. Very good. The Matt is asking, so I assume that the edge orientation values are dependent on the order that you decide to iterate through the over the cells, and this is just decided and calculated under the hood, like by the library, or how is it done?
Yeah, I mean, it depends in the order your neighbors are returned, basically, yes. It's calculated under the hood, so to speak. We prepare this in the driver code. So maybe if you're really curious, you're absolutely free to open up driver.cpp in any of the exercises and see how we calculate these geometrical factors. But this is just if you're really interested and if you can stomach some less than beautifully written C++.
Right, but would you agree that then this is a convention chosen somehow by the library, and the important thing is that you are consistent and you always use this edge orientation?
Yeah, I mean, it's a convention. Depending if you're using a different mesh library, you will get different geometrical factors. Maybe this helps. So if one meshing library decides to return the edges in counterclockwise order and the other meshing library decides to return the edges in clockwise order, then you will typically end up with different geometrical factors, which is also a nice way to be independent of the meshing library at hand.
Very good. At this point, do you want to clarify the meshing library that you are using for the driver, or are you going to explain that
Yes,
later?
I wanted to do this right at the start of the next exercise, actually.
All right, very good. Then we can postpone it. I think there are no more questions, so I guess that's fine. We can continue.